So now what I'm going to do is wire up the thermistor, and this is an example of one of the two thermistors that should be in your kit. Look like that. And it's a pretty simple wiring scheme. It would have been better again with alligator clips, but we can make it work with standard meter leads that look like this. So I'm actually going to tape it on. I have electrical tape. What I like about electrical tape is it really doesn't leave residue as much when it's undone, when it's pulled off, whereas other tape could more. And it's also a little bit more waterproof. But I'm going to be wrapping this in plastic anyway. So what I'm going to do is I'm going to take one lead and make sure it's touching the meter. I'll even wrap it around once or twice to make sure it's got a good electrical connection, because you want to make sure that that electrical connection is not compromised. So it's wrapped around, and then I'm going to wrap that with tape to make sure it stays connected. Wrap it tightly, and I'll be taking it off at the end and cleaning it, ideally with rubbing alcohol or something to get rid of any residue. And I'll do the same thing with the other side. All right, so you can watch me do it, but now you know what I mean when I'm doing that. And this is my simple temperature probe, which should affect the resistance, which I can measure with my meter. So I'm going to take the other end and wrap it like this. Oh, I want to first make sure I have a good electrical connection there. So I'm going to wrap it around. Hopefully it'll stay connected. Okay, so you see that? And then I take the tape and put it on there, wrap it well. There's my probe. Okay, so whatever this touches will affect the resistance, which I should then see on my meter. Now, what I'm going to do on my meter, I have to use my meter for two things, because your meter comes with a temperature probe. Your temperature probe looks like this. It's a piece of wire that has, it's the white wire that with the blue stripes that has these two probes on it. Now, if you didn't get the meter that is a temperature probe, you can use just a regular thermometer. In some ways that might be easier if you have one. In the absence of that, I'll give you some other suggestions, but it's really good if you can have a thermometer or something that can measure temperature. Your kit comes with a temperature probe and the setting of the meter, either degrees Fahrenheit or degrees centigrade. I'm going to be putting it at the moment on resistance. So I'll put it on the 20 kilo ohm scale, and I'm going to insert this here on the red one there, the black one here, and notice it gives a resistance associated with the temperature probe. Now watch what happens when I put my hand on the temperature probe. I'm warmer than the air around it. The resistance changes. Isn't that cool? So this, and when I take my hand off, it's going to go back to where it came from. Once it reaches some sort of an equilibrium with the environment, it'll stabilize. But at first it takes some time to adjust, so keep that in mind. And what I'm going to be doing with this temperature probe is I want to actually insert it in some plastic like this. Admittedly, that's going to keep some of the heat out, but when I don't really want to get it wet. The one that comes with your meter is okay to get wet. This one I'm not so sure, and I'd prefer not to have it short. So maybe okay to get it wet, but I'd rather not. So I'm going to wrap it in plastic like this when I actually dip it in something. But even when I still hold it like that, it still can tell that I'm warmer even through the plastic, and it'll adjust accordingly. Okay, so this is my temperature probe. Now what I want to do is I want to measure the resistance using my temperature probe and compare it to the temperature that I'm going to get using my temperature sensor, which is this guy, the one I already showed you. So if I use my meter to do both, I'm going to have to keep switching, which is fine, but keep that in mind because I don't have two meters. I have to use the same meter to measure temperature as I do to measure resistance. If you have a thermometer, you can have your thermometer going constantly and use your temperature probe that you just wired up along with your thermometer. and it might actually be easier, but I don't have that, so I'm gonna have to go this route. So I'm gonna switch this back to the temperature scale, and I'm gonna pull this out. So I'm gonna have to do this in between each measurement. Because at the moment, the first thing I wanna do is measure temperature. I'll keep it in degrees Fahrenheit because we're probably more familiar with that. Now it's saying that my room is about 64 degrees Fahrenheit, which is probably about right. Might actually be a little warmer than that. I'm not sure how accurate it is, but watch when I touch it. It should go up. Now it's not going to be 98.6 degrees that it's going to record because that's my internal temperature. I'd have to like swallow this or who knows what to get that kind of temperature, but you can see it's certainly going up. My skin temperature is certainly warmer than the room temperature, but not as warm as my internal temperature. That's why you often put thermometers under your mouth. I'm not going to put this in my mouth, but hopefully you get the idea. But what I am going to do, and this is something that I encourage you to do too, something like this, is I have crushed ice right here. Let's see if we can see it. Crushed ice and temperature. And what I actually did, two types of ice. One ice is not crushed, it's here. This is kind of interesting, just cubes. And the other one was crushed. It's hard to both see the temperature scale and the ice at the same time, but I'll do the best I can. And what I'm going to do is I'm going to dip this in here, and you should see the temperature go way down when I dip the in the ice water. It goes down to about 35 degrees. I could not get it to go below 35 degrees no matter what I tried to do. And with the solid cubed ice, it tended to be a little bit warmer than the crushed ice because the cubed ice has less surface area than the crushed ice, which is kind of an interesting aside. But what I'm looking for here is something that's going to give me a nice cold temperature that I can use to get one of my readings at. So I'm going to use the crushed ice and see if I can get, should be 32 degrees, if you remember, because the freezing point of ice is 32. But even with the crushed ice, I couldn't get it to 32. 35 is about as cold as it seemed to be able to go, no matter what I did. Couldn't get it below 35 degrees. So maybe it's the limitation of the temperature sensor itself, or maybe it's just that I don't have enough really crushed ice to get it to be right at the freezing point. But 35 is what I have there. What I want to do now is I want to stick my temperature probe in there, the one I just made, as opposed to the one that's actually giving me the temperature. I'm going to put this in there with the plastic, put it in the plastic bag and measure the resistance of, oh, almost went to 34, how exciting. But I want to measure the resistance of this. So I'm going to have to unplug this here. Put this on the resistance scale. Take my temperature probe out, put it on the resistance scale. 20 kiloohms, because that's about the value of my, that's around the value of my thermistor, what it's approximately going to be reading. It's reading 10.7 right now. Now when I dip it in here, it should definitely cool down, which means as it cools down, the resistance is going to change. Let's see what it becomes. Oh yeah, the resistance goes up as it gets colder with these. So we're going to let it get as cool as, I'm sorry, the resistance goes down when it's colder. So I want it to get as cold as it can. I want to record that value. It got so cold that it went to a different, let me see what happened here. What's going on? Okay, it went up. The resistance went up with the coldness. I apologize if I said that wrong. So I had to go to the next scale up. So I'm gonna let it sit there and get as resistive, as cold as possible, which means as high a resistance value as possible. Then I'm gonna call that what we know as equilibrium. That is basically the value it's recording. It looks like it hit 23.2. And now I'm gonna call that 35 degrees. So it's 23. It's going even beyond that. So when it gets to whatever maximum value it gets to, I'm going to record that in my table. And remember, it's in kiloohms. And I'm also going to record the temperature that I recorded with my thermometer. Wow, it's past 24. Okay, so this is close to the freezing point of water. 24.1, 24.2. I'll let it do that for a while, and you'll do the same thing. Then what I'm going to do is I'm going to pick some water of a different temperature. So I'm going to get some tap water. That's basically, well, I don't even have to use water. I can just take it out. So I'm going to take the whole thing out. So you might want to let it sit longer than that, but mine went up to 24.2 or something like that. Now I'm going to let it come out and adjust to room temperature, which if you remember a few minutes ago, I measured that to be about 60, and I can adjust down to this scale here. I measured room temperature to be 64 degrees. So whatever resistance this becomes, on one column, I'll say it's 64 degrees, then it's going to be whatever resistance this is, which should go down to around, 10 kiloohms or something like that. That's what we saw earlier. It's still warming up. Remember, it got quite cold in there. It takes a little while to warm up and get back down to the resistance it had earlier. My goal is to get a few different values of temperature that I can use to see what my thermistor is recording as far as resistance and how it varies with temperature. That's what I want to look at. The more points I can get, the better. Right now I'll get 4 points. I'll get this ice water, which we measure to be about 35 degrees Fahrenheit. I'll get room temperature, which we measure to be about 64 degrees Fahrenheit. I'll get some lukewarm water like tea that I have here, which I just warmed up, but it's not boiling. And I'll get some hotter water. So the more different variations you can get, the better a curve you can get to see where your temperature lies and how it affects your thermistor resistance. But I'm going to wait for this to do its thing for however long it takes right now. But hopefully you're getting the idea, and I'll do one more with you so you can see that thermistor should get lower than it had originally when I start getting to higher temperatures, like the 84 degrees of my skin. You could use that for that matter. You can say, oh, my skin's 84 degrees, and if I hold the thing, what's its resistance? So the more standards you can get, if you like, or the more measured values of temperature you can get, the better your result will be in the end. Now, if you don't have a thermometer with you, what you could do is you can say, okay, ice water when it's in equilibrium. In other words, if I have a lot of crushed ice in water, it should be about 32 degrees Fahrenheit. Again, we got 35, but it should be 32. So that could be a standard you use for your thermistor, that it's at 32 degrees Fahrenheit. The other thing you could do is you could get boiling water. Now, for safety reasons, I'm not going to encourage you to use boiling water. Pure water boiling should be 100 degrees Fahrenheit. I'm sorry, 212 degrees Fahrenheit, 100 degrees centigrade, but 212 Fahrenheit. But I'm not going to encourage that because boiling water can scald you. So I don't want you to be doing something that can cause you to have an injury. So it's better if you can get a thermometer and make a temperature measurement and then calibrate that to your thermistor accordingly. Now it's taking a while for this to reach room temperature, but this is going to continue to go down. You can see it hasn't reached the equilibrium yet. It's still warming up as time goes on. It's still dropping and dropping and dropping. It'll continue to do that. Once it reaches whatever value it's finally going to reach, that's the value I'll take. It's interestingly, when I touch it, it dropped immediately. You saw that because I'm so warm. Now it's going back up to whatever value it is associating with room temperature. It looks like it's more like 11 degrees. I'm sorry, 11 point something kiloohms. So that might be its equilibrium value. So you'll wait for it to get to that temperature. Now, I have some lukewarm tea here. So I'll show you what I'll do with that. It's the same thing I'll do with the ice water, but hopefully you'll get the idea. Here's my tea. It's green tea. I'll take another sip maybe before I do this because I don't want to drink it after I put the temperature sensor in it. And I love my green tea. But it's definitely warm. It's quite warm, but it's not boiling. I could drink it without scalding my mouth. So what I'm going to do is I'm going to put my temperature sensor in there. Again, that's this guy. It's the one that came with the kit. And I'll plug it in. Turn this to the temperature scale. I'll go with degrees Fahrenheit, so we're all talking the same thing. And this one I can put in the water and it's fine. And it looks like it's recording about 128 degrees. Okay, it would be pretty warm. Wouldn't last long in there if we were in a hot tub. 128 degrees, pretty warm. I can drink it though, it doesn't scald me. All right, now what I'm going to do is I'm going to put in my new temperature sensor, the one I just built, and put it in a plastic bag. And what had been 128 degrees, whoop, I can't go with this. I have to go with kilo-ohm scale. Okay, and you can see the voltage is dropping as it does now with warmer temperature. Not the voltage, I'm sorry, the resistance is dropping with the warmer temperature. So now it's 4 point something kilo-ohms, it's getting warmer and warmer. But I'll let it come to some sort of a stable point, and I'll record that as the resistance that I associate with 128 degrees Fahrenheit. Looks like it's going to be around 3.7 something kilo-ohms. Maybe even lower. Let it do that for a little bit more. Stir it a little bit to try to get it equilibrated. Looks like around 3.6. Okay, so it's 3.64 kilo-ohms, 3.63. So we're going to take that value and record it, or 3.60. It's going to the 3.5 range now. But that's our 128 degrees. All right? Now I have even hotter water here. I should do the same thing. Here's my teapot. This probably would scald me. It's not boiling, though, anymore. But if I use my temperature sensor, I could do the same thing. Here's my teapot. Take the lid off of it. You can see the tea leaves in there and all that good stuff. I'll have to wash this well when I'm done. But watch how low it goes now. It's probably going to go much lower, I would suspect, than I just had. Yep, it just passed it. It's lower. Okay? So if I recorded the temperature here, it would probably be quite a bit warmer. But you see, I'm coming up with a way to calibrate my thermistor so that I can tell what my temperature, what resistance it corresponds to for my thermistor. And this gives me a way to measure the temperature of any object that I put the thermistor in contact with. It's still equilibrating, but it looks like it's below. It's going to be probably around, maybe even less than 2 kilo-ohms at this temperature. Close to 2 kilo-ohms. But I don't know what the temperature is of it. I should put the lid on it so it stays. Ooh, just dropped a bit more. So it's below 2. And I'm just really curious. I want to see what my temperature is once I do this. Around 1.8. Drop below 1.8. Is it going to do it? Yes, it did it. So if I let that equilibrate a little bit longer, I'll get a value. Looks like around 1.75 or so. And then what I'm going to do is I'm going to put my temperature sensor in there. Might even go a little bit lower than that in terms of the resistance, but it's close to 1.75 kilo-ohms. Oh, 1.74. But you can see it's slowing down the rate at which it's changing. So it's going to reach a stable point pretty soon. It won't just keep going down. Maybe more like 1.7. Okay, I saw it go down to 1.71. So I'm taking out my temperature sensor. There it is. It was protected, remember, inside of this. All right, and let's see about what, and of course, its temperature is changing as I take the lid off and switch sensors and all that, but I'm going to do it anyway. Knowing that I'm doing the best I can, and so are you in the circumstances we have. So back to degrees Fahrenheit. Here's my temperature sensor. Here it goes into the hot tea. What is the hot tea telling me? Yeah, there we go, 100 and... Might have even been warmer a minute ago when I was doing all this. but about 157 degrees Fahrenheit. Okay, so it's definitely less than boiling, but quite a bit warmer than the lukewarm tea. But we have a few points there that I could then use to try to calibrate everything. And again, the more points you have, the better the curve you'll have. The better you'll be able to see how your temperature sensor, or I'm sorry, your thermistor, its resistance varies with temperature. All right, and fill that out, and then there's some questions in the lab and some graphs that you'll do, and then you'll be ready to actually build a circuit next week that will measure temperature using voltage, using the same sort of setup we had involving voltage division. Okay.